So last week, which seems like forever ago now, after that long weekend, we just talked about the basics of probability. General probability is calculating what you have or what you want to happen out of the total things that can happen. Today, we're going to talk about conditional probability. Conditional probability is the probability that one event will occur given that another event has already occurred. And this is the notation that we're going to use for it. So again, we're going to see a P with a parentheses to represent probability of, and then I would read this event B given event A. And B and A can be different things depending on what you're calculating the probability of. It might be like you're drawing colors out of a hat. So it might be the probability of red given green, meaning the probability that I'm going to select something that's red given that the last thing I selected was an item that was green. Okay, so the last thing in the parentheses is what's already happened, and the first thing in the parentheses is what you are calculating will happen. Sometimes event B and A affect one another, sometimes they don't. So we're going to talk in a little bit about what makes events independent versus dependent, because that's going to change how you actually calculate your probabilities. Okay? All right, so we're going to do these two examples together. Yeah?
Can you go back to real quick?
Oh, yeah. Yes, I can. Mm-hmm.
This McDonald's,
Mm-hmm.
on here it's saying like, it says your domain is not available.
I don't know.
I
I don't know why William.
I like login.
Okay.
So you cannot sign you in with this credential because your domain is not available.
That was the same error you had.
Yeah.
Okay. All right. Well, just use some pencil paper. You guys can always grab another. Are there any more in there? No. There's one more. Let's see. Starting right now, guys? You have your
Step up their game, bro. I scared myself. 85 and 77, man, y'all like this.
Here, Johnny, you try this one. Here, we'll play musical computers for a minute. We are going to get to our lesson, I promise. I wonder if it would let me log in.
Yeah, just
Yeah.
something like that.
And then he has this hamburger. Oh, yeah.
Yeah, I just want Danny
Mine's
$100
working.
because he got a referral.
Previously
So
cited
they're
on this
paying
device
$100
with another
for training.
credential.
Yeah, no, he's pretty happy with that.
People would have known long ago.
From orientation.
Yeah. I'll restart it. I'll just leave this one out for now. Are those other ones getting in there, guys?
It says it's preparing windows.
Okay, that's a good sign.
Yeah, this one is.
Alright. Alright.
Not good.
Will, do you want to share that Jamboard with Kyle?
Sure.
You guys can share. You guys are good. It's getting in there. We're okay? All good? Troubleshooted? Perfect. Okay. All right, so let's do these two problems together, and then on the next slide, you guys will have a couple you can try on your own. So here we're finding a conditional probability. The first example says 2 cards are selected from a standard deck of 52 playing cards. Find the probability that the second card is a queen, given that the first card is a king, and we're assuming that the king is not replaced. Often when you're talking about decks of cards, they're going to talk about replacement or not replacing, because when you draw something, you can either leave it out of the deck or you can put it back in the deck for the next draw. All right, so we are calculating the probability of a queen given a king. So here's how I would write this in notation. Queen given king, or they just might use like a Q and a K to represent that. So the question is, when I draw the king and I leave it out of the deck, does that change the probability of a queen that is drawn on the next selection? Yes, okay. Now we know the king has already been selected, so that's 100% certainty that that is happening. You can put a 1 there if you want to, but that's not going to change our answer. All you have to do is calculate, assuming that has already happened, what is the probability that we're going to get a queen? Well, how many queens are left in the deck if I took a king out? Queens, 4. And how many cards total are left in the deck? 51. So that's our conditional probability. There are 4 of each thing in the deck. How many of each, face card or number or whatever? How many of each suit, like hearts, kings, diamonds? 13 of each. These are going to come up in problems. How many face cards are in a deck? Do you know what a face card is? There are 12. It's anything with a face. So jacks, queens, and kings. And there's 4 of each of those. So there are 12 face cards. Okay, so 4 out of 51. And if I turn that into a decimal, usually we give it like 3 decimal places, 0.078. Okay. All right, the one below. Table shows the results of a survey in which 2,276 social media users were asked whether they have been offended by something, posts, comments, or photos that they saw on social media. Find the probability that a user is male, given that the user was offended by something on social media. Okay, so we are calculating the probability that we select a male, given that they were offended. Okay, so again, we know that this person was offended by something on social media, so we don't need part of this information. The answer is yes, they were offended on social media, so these 2 other columns are extra information. We know that they fall in the first category. We are given that. Then from that column, we want to find the probability that the user is male. So we are only using information from that column. So often when you see these tables, you'll use either a single row or a single column based on your given information. What's the total in that yes column? 1151. And how many males are in that yes column? 532. Okay, so the probability that we're selecting a male, given that they're offended, is all the people that were offended and the males that were within that smaller group. So 532 divided by 1151 to 3 decimal places is about 0.462. Okay, does that make sense? Good? Okay, the next slide on your Jamboard has 2 questions for you guys to try based on this table of information. Okay, so I'll give you a couple minutes. You can work together if you want. Find these 2 probabilities. The decimal in the last one was a 0.462 when I divided those. Okay, you should get 0.464 and 0.552. I heard Ryan say the given is what you're dividing by. I think that's a good way to put it. Given is what you're dividing by, that total. Okay, so like the first one, you're given that they're a male, so the male total is what you're dividing by. And then the other one is within that first row there. And then the second one, you are given that they contribute. So the total people that contribute are 259, and then the females within that are your numerator. Okay? Any questions on those? No. Okay, moving on. All right, so let's talk about what is an independent event. It's exactly what it sounds like. Things are independent events from one another if they do not affect one another. So examples of events that are independent are tossing a coin and rolling a, they use the word number cube here, but dice. Okay, so if I toss a coin, that has no effect on what's going to happen when I roll the dice. And maybe rolling a dice multiple times in a row, for example. If I roll a 3, that doesn't mean I'm more likely or less likely to roll a 3 on the next roll. One dice roll does not affect the next. At the bottom here, you really don't need to write this down. This just says if two events are independent of one another, the probability of one does not affect the other. So when we say the probability of given A, B given A, but A doesn't affect B, it's just really the probability of B. A has no effect on it, so we're just calculating the probability of B and vice versa, okay? So the first thing that we're going to do with this is we're just going to look at sets of events, and you might have to skip forward. Is it the next slide? Skip ahead to 2 slides where it says classifying as events as independent or dependent. All we're going to do is look at these 2 events, and we'll do the first couple together, decide if they're independent or dependent, okay? And then that'll talk about later then how we're going to actually calculate the probability based on that. So the first one says we select a king from a deck of 52 playing cards, not replacing it, and then select a queen from the deck. So does selecting a king, not replacing it, and selecting a queen then, does that affect the probability of selecting the queen? Yes, the fact that we have not replaced it changed my denominator. It's not a 52 anymore, it's a 51. So because the first event affects the second event, we say that those are dependent events from one another, okay? Tossing a coin and getting a head, and then rolling a dice and getting a 6. Those are independent. One does not affect the other. Okay, driving over 85 miles per hour and then getting a car accident. So here you kind of have to make a little bit of an assumption, but do you believe that if you drive more than 85 miles per hour, that would affect the probability of you getting in a car accident?
Yes.
More than likely, the probability would get higher for the second one because you're driving faster. So we would say that those are dependent events. Okay, what about smoking a pack of cigarettes and developing emphysema? More than likely dependent. Okay, and then tossing a coin and getting a head, and then tossing a coin again and getting a tail. Independent events. Good. Questions? Great. Okay, so the multiplication rule for independent versus dependent events. If you have dependent events and you want 2 things to happen back to back, like our queen-king example, okay? I want to select a king, and then I want to select a queen. I first calculate the probability of getting my king, and then I multiply it by the probability of selecting that queen, given that I've already selected the king, okay? That's if they're dependent events. If they're independent events, one does not affect the other. So all I have to do are multiply their independent probabilities together. The second probability is not affected by the first, which is why you can see the notations are really similar. We calculate the probability of the first event and then the probability of the second event. This one is slightly different though because it's dependent on that other thing that's already happened. Okay, so when you have, we're going to think of this as 2 events happening simultaneously, back to back. You're going to calculate the probability of one, calculate the probability of the other, and then multiply them together. That's why I call our multiplication principle. All right, so here's our queen-king example. We have 2 cards selected. Without replacing the first card, we want to find the probability of selecting a king and then the probability of selecting a queen. Okay, so what is the probability of selecting a king? 4 out of 52. Okay, and then we do not replace. And then we select another card and we want to know the probability of getting a queen. So how many queens are in the deck? 4, assuming we got that king out already. And how many cards are left? 51, and you're just going to multiply those fractions together. Now you can do this a couple different ways. You can multiply the whole fraction together, or you can just multiply the numerators together, the denominators together, and then divide last, however you want to do it in your calculator. But again, we're just probably looking for that decimal. Okay. So I get 0.006 about. Okay. And those were, by the way, dependent events, because that second fraction changed based on the first event that happened. All right, a coin is tossed and a die is rolled. Find the probability of tossing a head and then rolling a 6. Are these independent or dependent events? They are independent events. What's the probability of tossing a head? What's the probability of rolling a 6? And nothing weird happens with either of those because they do not affect the other. So you could say 1/12, and then you can divide it and get the decimal, 0.083. Okay, probability that a salmon swims successfully, it's a mouthful, through a dam is 0.85. Find the probability that 2 salmon swim successfully through the dam. Okay, are these independent or dependent events, do you suppose? So from what we're given, we need to assume that these are independent. If they were dependent, we actually wouldn't be able to answer this question because we don't know then if one salmon gets through, if that affects the other one, we wouldn't have that other probability to use. All we have is the probability of one salmon swimming through. So we are to assume that they are independent of one another. If they're independent of one another, you just calculate the probability of each of them and then multiply those together. So salmon number 1 has a 0.85 chance, salmon number 2 has a 0.85 chance, multiply them together, and that's the probability that both of them will get through. Okay, so 0.85 times 0.85, I get 0.7225. I don't have to round that one. Okay, 2 cards are selected from a standard deck of 52 playing cards, again, without replacement. Find the probability that they are both hearts. Is this independent or dependent? In this section, this is dependent, okay? What's the probability that the first guy selected is a heart? 13. Okay, out of 52. And then that heart is not replaced. So now for the second one, it's going to change. How many hearts are left in the deck? 12 out of 51. Yep. And then multiply them together. And I get 0.059. Good? Questions? Okay. I'm going to give you a couple to try on the next page. Okay. All right, here it says an ACL reconstructive surgery. Did you get one of those, Kyle? You've had a few. Okay. The probability that the surgery is successful is a 0.95. So if the probability that the surgery is successful is a 0.95, what's the probability that the surgery is not successful? The complement? 0.05. Okay, so you really have 2 probabilities in this set of information. All right, see if you can do those 3. Go ahead. I'll give you a minute. All right, so 0.95 to the third power for the first one, you get 0.857. For the second one, 0.05 to the third power, which remember that e-4, if you're doing that in the graphing calculator, means times 10 to the -4th. So that decimal is 4 spaces to the left. So you get a really small decimal there. And then number 3 is tricky. When it says the probability of at least 1, there's a lot of different ways that can happen. The first one can be successful and the other 2 are failures. The middle one can be successful and the first and last are failures. Or the third one can be successful and the first 2 are failures. Or 2 out of the 3 can be successes and 1 is a failure. And there's a few different ways for that to happen. So one way to do this problem is you calculate each of those individual probabilities, all the different ways that at least 1 works, and then add them all together. And that would give you the same answer. but it is easier to recognize that the complement of at least one is none. Okay, if I see at least one was successful, that is the opposite of nothing being successful. Something is the opposite of nothing. Does that make sense? So that's what this little note at the bottom is. You might want to write that down. The probability of at least one is the complement of none. The probability of at least one event occurring is the complement of no events occurring. So that can save you a lot of time instead of finding a lot of different ways for something to happen and adding them all together, just recognizing that two things are opposite. Okay, any questions on this? Okay, I got one more slide for you and then we're done for the day. Okay. So in the last chapter, we talked about an event would be considered unusual if it was more, or a probability would be considered unusual, or a data value would be considered unusual, or an outlier if it was more than 2 standard deviations away from the mean. When we're talking about probabilities, we say that a probability is unusual if it is less than 5%. Is the likelihood that it would happen. So something with a 3% probability would be considered unusual, and something with like a 7% probability would be considered a usual value, okay? So we're going to answer a couple of these real quick and just determine, based on the probability we get, is it a usual or unusual event? So this says, in a jury selection pool, 65% of the people are female. Of those 65%, 1 out of 4 works in the health field. First thing we're going to do is find the probability that a randomly selected person from the jury pool is female and works in the health field. Okay, so let's start with the probability that the person is female. What is that probability? 65%. So 0.65. Times then that they also work in the health field. So this is dependent. We are given that they're a female. What is the probability that they work in the health field then? 25%, or you could say 1 out of 4 if you want to. 0.65 times 0.25. I get 0.1625 is my probability. Is it unusual? It's not less than 5%, not unusual. I can spell. It'd be great. There we go. All right. Second one, find the probability that a randomly selected person from the jury pool is female and does not work in the health field. So what's my first number going to be? 0.65 again, but they do not work in the health field. So if 25% do, how many don't? 0.75 or 3/4. So just using the complement there. And I get 0.4875. Unusual or not unusual? Not unusual. Okay. That's it for 3-2. All of our conditional probabilities. All right. So 3-1 Math Excel is due tomorrow night. 3-2, this assignment is due on Friday night. Okay, so I'll go back to that slide in a second here. So those are your 2 deadlines for this week. You've got 1 Math Excel due on Wednesday and 1 Math Excel due on Friday. So we're going to do 3-3 and 3-4 the next couple days here. I have a circuit training bonus for you guys for chapter 3, like we did for chapter 2, if you're interested. This is due March 7th. It's on your calendar, so like about 2 weeks from now. Some of this you can do already. Some of it is stuff we're going to talk about over the next couple days. So you can hang on and do it all at once if you like. That's fine. Did I tell you that I have jury duty? Yes. Yes. Okay, that's next week. Potentially. So I apologize in advance if I'm not here for multiple days in a row, because you know I have 0 control for that. So if you have to watch videos, guys, do your best. I will be available via email like this evening, so I'll get back to you if I can get it up there today. March 7th. And yeah, I have stuff from last semester. Yeah.
Like, just the, we leave like Friday, like, break that Friday,
Oh, yeah.
and we quit, that's 2 weeks,
Yep.
but we just learned a lesson the day before, like, throw away,
Yes.
just go from last, like.
Yeah,
last
that was
semester.
probably like over no burner.
Yeah.
Yeah.
Because it's open on division, so
Okay.
I just take the study hall the day before.
So you're not gonna be here that Friday?
Yeah, I won't be there Friday,
Gotcha.
but my study halls are before this period.
Yeah, so
So
you
if I
can
was
take
gonna
it
take a
then if
study
you
hall,
wanted
I'd
to, or
rather-
you can take it when you get back.
I just didn't know, like.
Yes, I do. Just wanna watch the video from last semester. Yes.
One that shows how you can find.
I mean, we only need a few more flips, shouldn't be that hard.
I don't know what else we need, that's why I didn't do it.
Well, we need to write up a